Where I'd like to start today is not doing this because I think we've done enough of these. I was called out by one of you last night. It was, I don't know, the middle of the evening. And after I told you, do the homework earlier and get on it and don't be lazy and a bum and all that. And then I forgot to post what the homework assignment was. So I apologize. It is now on there. Like I say, the beginning, if you even just flip through the exercises at the beginning of the end of the chapter, then there's questions like this, as you saw. So let's move on now, and we're going to look at this term now. That's kind of where we're going to land and park for the rest of the chapter, is on that term right there, the heat. The heat that's going in and out. If the system is a chemical reaction, then we can still use this, but we're going to have a different name for that Q. That name is enthalpy. The heat that goes in and out due to a chemical reaction is the enthalpy of the reaction. Yeah, at the end of it, I'm hoping that you can follow kind of where I came up with this expression. If we have this from yesterday, the total internal energy, we're calling Q delta H, and remember work is negative P delta V. So all I did was I took this relationship and solved it for delta H, moving the positive P delta V over. Now, P delta V is the same thing as delta PV. And the reason I moved that delta term is we've learned, and now we know very well, what PV is equal to from the last chapter. PV equals what? nRT, right. And I mention that because there will be times that you'll have to know the relationship between delta E and delta H. And the relationship between those two terms is they're kind of they're separated from each other, or they're different from each other by that term, the delta PV, or, because of the ideal gas law, the delta nRT. Now I know that there are questions on the practice test about that relationship between delta E and delta H, so you'll need that. And what we use this for, if you have some reaction that generates a gas, maybe you start with a solid and you heat it up, and you produce a couple moles of gas. Well, when you produce a couple moles of gas, the system is going to expand. And as it expands, it will be doing work on the surroundings. We talked about that yesterday. Well, if you look at this, what does that do to your delta E? Just like what happened yesterday, if you're doing work, you're using up some of the internal energy, and that means that the more moles of gas that you're making, the more you're pushing back on the atmosphere, the more of the internal energy you're using. So that value goes down. So that's the kind of thing that we use this for. This again, we're really going to focus on this. The rest of it is more physics concepts, but that entering and exiting of heat in a reaction, that's going to matter a lot. So we have this. The delta H of a reaction is always, delta always means final minus initial. So when you have a reaction, the delta H of the reaction is the amount of heat of the products minus the amount of heat of the reactants. So I'm hoping you remember some of this from Chem 1. When we start calculating delta H, you did some of that in Chem 1, I think. Knowing that a positive delta H means the reaction is endothermic, negative delta H means it's exothermic. So how do we find delta H? Now I do have to say, remember, as we talked about yesterday, we don't know, it's not physically possible to determine how much heat something contains. A reaction or an object, we don't know how much heat is in there. All we can measure is how much heat is either going out or coming in. And so these are not really measurable quantities, but we can actually find the delta H of a reaction. There's two ways that we can find delta H theoretically. And theoretically means without making any measurements, just using accepted values for things. So we're going to go through that today, the two ways that we can find delta H theoretically. The first way that we'll do it is using the book, and that's why there's books scattered around the room. If you walked in here and saw the books and thought, oh, do we have a reading quiz today? It's not for that. It's for referring to. There's a heat of formation table in the appendix of the book. And when you're done writing this out, I want you to turn there if you have a book near you. Now this definition is going to turn out very important. You need to know that. So I'm going to recommend that you actually write this down and either put a circle, a cloud around it, a box, or highlight it. I want you to know what the definition of heat of formation is. That heat of formation table starts on page 819, but it's right at the bottom of 819. If you turn the page over to 820, you can see that it takes up a few pages. I'll go back to that. But yeah, you have 2 columns per page, and in each column, there are 3 columns. So yeah, you can see there's column 2 on that page, column 1 is over to the left. And what we find is that the 3 columns within each column, one is the heat of formation table. That's the only one that we're going to use in this chapter, is the heat of formation. In chapter 17, when we do thermodynamics, we'll have the delta G, Gibbs free energy, and then the delta S. You remember what delta S represents? Entropy. Yeah, it's entropy. Yep. So those are thermodynamics topics. You just wrote down what the definition of heat of formation is. That's what this first column is going to tell us. And what that means is this. For each of those, when we make 1 mole of that substance from its element, or elements, that's how much energy is either taken in or given off. So you can see what the unit is, kilojoules per mole. So you need 1 mole. So for instance, the HCl. If you make 1 mole of HCl from hydrogen and chlorine, it would give off 92 kilojoules. So it actually, if you have a negative heat of formation, that just means that when that substance was made, energy was given off. And anytime in science you have a chance to give off energy, it becomes more stable. And so, like, look at what is that, Cr2O3. It's got a heat of formation of negative 1,128 kilojoules. So when you make a mole of this, you give off a huge amount of energy. 1,000 kilojoules is a lot of energy. It's like a megajoule of energy. 1,000 kilo of something. That's a lot. And that just means that that is a very stable compound. Some things have a positive heat of formation. You do see some zeros in there. You may remember the zeros. Zeros represent the actual elements because they're not made from their element. They are the element. So they don't have a heat of formation. They're 0. Sometimes you have a positive number. And the positive ones, like this one, 217. Oh yeah. Hydrogen gas, but not diatomic hydrogen. Hydrogen naturally exists as H2. But if you have just H, what you have to do is you have to take a mole of H2 or a half mole of H2 and split the atoms apart from one another. And to make 1 mole of hydrogen atoms, you'd have to take H2 and put in 217 kilojoules of energy to get those all to split apart. So anyway, that just means that when you have a positive delta H, that is not a stable compound. That means you had to beat up on it, add energy to it to get it to be made. Nature does not tend to want to take in energy, it wants to try to get rid of energy. Okay, so what I'm going to do is ask you to try a couple of delta H problems involving heats of formation, and that's why I've got several books around the room. Let's try this one. Would you find the delta H for this is not actually even a chemical reaction. This is just a physical change. It's ammonium chloride solid dissolving into ammonium ions and chloride. But you can still find the delta H for this even though it's not a chemical reaction, just from looking up the heats of formation of each of these. So to find delta H, you're going to look up the values of these, take the products, the total of the products, minus the total of the reactants,